In this paper, we propose a novel framework to simulate multi-domain subspace deformation in real time. The deformed object is decomposed into several subregions called domains, and we construct subspace at each domain instead of the entire deformed body. The deformation subspace is constructed with a novel boundary-driven approach. We generalize the boundary displacement geometrically and minimize the system's potential energy with respect to the boundary constraint. The rigid boundary mode takes advantage of the linearity of the infinitesimal rigid body motion and constructs the corresponding subspace with small size. We also use manifold harmonics to represent the interface deformation when the boundary is soft and large. The domain coupling becomes trivial and can be achieved by using the Lagrange multiplier method. On the top of the boundary mode, vibrational modes are also incorporated in order to capture the internal deformation induced by the accelerated body movement. The large deformation is handled with per-node co-rotational elasticity with model reduction. First, we show how soft boundary modes improve the simulation. If an interface is small, the rigid interface fitting, as used in deformation substructuring, is a reasonable approximation. Interface deforms with high rigidity, and the soft boundary modes do not bring notable visual improvement. However, when the interface is wide and soft, the rigid interface assumption could induce artifacts. We can see discontinuous deformation across domains interface. Soft boundary modes capture the interface deformation well and produce smooth result. Next, we evaluate the accuracy of the proposed method. Here, we quantitatively compare the result of our method as well as other popular simulation techniques. From right to left, each bar model is simulated with nonlinear full space simulator, model derivative, deformation substructuring, model warping, and our method with only rigid boundary modes and with both rigid and soft boundary modes. The figure shows the average y-direction displacement at the freed end of the bar models. We compare results of our method and the multi-domain character scanning using nonlinear subspace with the smaller number of modes. Cracks are visible between domains with penalty forces. They disappear when the number of modes increases, where our methods guarantee seamless domain coupling even with small number of bases. Next, we compare our method with deformation substructuring using rigid interface fitting. The Tyrannosaurus model is decomposed into 17 domains with over 120,000 tetrahedron elements. We can see that with large deformation, pure rigid interface fitting will also induce cracks. Such cracks can be fixed by using geometry blending at the post-simulation stage. While such post-simulation processing is not required using our method, as domains are always seamlessly coupled. Our method is able to handle large deformations. The sunflower model consists of over 47,000 elements and is decomposed into 13 domains. Leaves are signed with higher-order inertial modes and a softer material, and they have enriched local deformations. Our framework also supports direct user manipulation. The fish model consists of 110,000 elements and 10 domains. It can be manipulated in real time by the user. Two interfaces are also manipulated by assigning the interface orientation, and natural deformation can be simulated. Finally, we show a C-ball model with over 250,000 elements and 24 domains. Domains connection forms 7 loops. It can also be interactively manipulated with the user. Highly stiff material is assigned to the masts, and the softer material is assigned to the canvas. We also applied high-order inertial modes to the canvas for enriched local deformation. We apply scripted forces at the masts and wind force field at the canvas. Interesting result can be simulated. Thank you.